Now we've just done a series stub match. Let's consider a parallel stub match. In this case, again, I have ZL, and I'm going to move a distance D to match my line, and then I'm going to add in a parallel stub. And this time, let's do a parallel stub with a short circuit on the end. And what I want to know is the length that I need for this stub. So the first thing that I'm going to do is normalize and plot my ZL. Let's just use the same one. 2 plus J2. So again, that is right there. There's my ZL. Now what I'm going to do is rotate, actually the easiest thing is I can see that I've got a stub that's in parallel, so it's going to be easier for me to add admittance at this point. I might just as well convert to admittance right now. So let's just take ZL and translate it through the center of the Smith chart. Here is my distance right there. Mark from here to here on your paper. Bring it from the center to right there. This is my YL point. Now I'm going to rotate YL until I get the real part matched. That's the same matching circle that I had before. It's right here. That's the real part. It's equal to 1. So I'm going to rotate YL, make a note that I converted that to YL, rotate YL towards the generator to the matching circle. So here I am rotating towards the generator. Here we go around towards the generator. Again, if you had a protractor, put the center of your protractor right here, put the pencil part, and draw your circle. But as usual, I didn't bring my protractor, so I'm going to use just a piece of paper. I'm going to center it here at the center of the Smith chart, and then I'm going to line up my distance right there. So this is going to be YA. There's going to be another choice over here. Again, line up at the center like this and mark the distance right there on the matching circle. So here's YA1 and here's YA2. I'm going to use YA1 again because I'm going to go for the shortest distance. So this right here is the distance that I need to calculate. Let me show you another way to calculate distance that helps to make it easier whenever you start to cross this line right here. What I'm going to do is add this piece first. So distance is going to be 0.5, 0.5, and this value, if I'm doing the towards the generator, is about 0.455. So that's that one little piece. And then I'm going to add in this piece, which when this comes here, it's about 0.175 plus 0.175 wavelengths. I guess it's getting late. So that's my distance D. Now my real part is matched, and I need to find out what kind of imaginary value I'm going to match. What I'm going to do right now is change to a different color of pen because I'm going to be doing this stub, and it acts like it's sort of like a different transmission line. So let's read off the imaginary part of YA. It's about 1.6. I know that I want Y stub to equal minus JX. So instead of 1.6, I'm going to come down here to minus 1.6. And I'm going to call that Y stub. That is Y at the input of the stub. So let me mark that by drawing a line straight through it. And then I'm going to rotate towards the load of the stub, to Y short circuit. Y short circuit is over here. So let's rotate towards the load this distance right there. And we can read that L is equal to, read on this inside curve right there, 0.25, my final destination, minus the value that's right there, which is about 0.165 wavelengths. So that's my distance L. If you were asked to design a parallel